Sustainability measurement is the quantitative basis for the informed management of sustainability. The metrics used for the measurement of sustainability are still evolving. They include indicators, benchmarks, or audits, indexes and accounting, as well as assessment, appraisal and other reporting systems. They are applied over a wide range of spatial and temporal scales. Some of the best-known and most widely used sustainability measures include corporate sustainability reporting, triple bottom line accounting, and estimates of the quality of sustainability governance for individual countries using the Environmental Sustainability Index and Environmental Performance Index, an alternative approach used by the United Nations Global Compact Cities program and explicitly critical of the triple bottom line approach's circles of sustainability. Sustainability indicators and the function. The principal objective of sustainability indicators is to inform public policy making as part of the process of sustainability governance. Sustainability indicators can provide information on any aspect of the interplay between the environment and socio-economic activities. Building strategic indicator sets generally deals with just a few simple questions. What is happening? Does it matter? And are we reaching targets? Are we improving? Are measures working? And are we generally better off? One popular general framework used by the European Environment Agency uses a slight modification of the Organization for Economic Cooperation and Development (DPSIR) system. This breaks up environmental impact into 5 stages. Social and economic developments drive or initiate environmental pressures which, in turn, produces a change in the state of the environment which leads to impacts of various kinds. Societal responses can be introduced at any stage of the sequence of events. Metrics at the global scale. United Nations indicators. The United Nations has developed extensive sustainability measurement tools in relation to sustainable development as well as a system of integrated environmental and economic accounting, benchmarks, indicators, indexes, or auditing, etc. In the last couple of decades there has arisen a crowded toolbox of quantitative methods used to assess sustainability, including measures of resource use like life cycle assessment, measures of consumption like the ecological footprint, and measurements of quality of environmental governance like the Environmental Performance Index. The following is a list of quantitative tools used by sustainability scientists. The different categories are for convenience only, as defining criteria will integrate. It would be too difficult to list all those methods available at different levels of organization, so those listed here are it for the global level only. Benchmarks. A benchmark is a point of reference for a measurement. Once a benchmark is established, it is possible to assess trends and measure progress. Baseline global data on a range of sustainability parameters is available at List of Global Sustainability Statistics. 2010 Biodiversity Indicators Partnership Indices. A sustainability index is an aggregate sustainability indicator that combines multiple sources of data. There is a consultative group on sustainable development indices metrics. Many environmental problems ultimately relate to the human effect on those global biogeochemical cycles that are critical to life. Over the last decade, monitoring these cycles has become a more urgent target for research. Auditing. Sustainability auditing and reporting are used to evaluate the sustainability performance of a company, organization, or other entity using various performance indicators. Popular auditing procedures available at the global level include ISO 14000, ISO 14031. The natural step, triple bottom line accounting, input-output analysis can be used for any level of organization with a financial budget. It relates environmental impact to expenditure by calculating the resource intensity of goods and services. Development and NGO project auditing. Litmus test type indicators are also used in the development and NGO community to test conformity and compliance with the guidelines of Sustainable Human Development and the International Rio Declaration of 1992. Sustainable Development Indicator for NGOs and other organizations. Reporting Global Reporting Initiative Modeling and Monitoring Procedures. Many of these have only just been developed. State of the Environment Reporting provides general background information on the environment and is progressively including more indicators. European Sustainability Accounting. Some accounting methods attempt to include environmental costs rather than treating them as externalities. Green accounting. Sustainable value. Sustainability economics. Resource metrics. Part of this process can relate to resource use such as energy accounting, to economic metrics, a price system, values as compared to non-market economics potential. For understanding resource use, an important task for resource theory is to develop methods to optimize resource conversion processes. These systems are described and analyzed by means of the methods of mathematics and the natural sciences. Human factors, however, have dominated the development of our perspective of the relationship between nature and society since at least the Industrial Revolution, and in particular have influenced how we describe and measure the economic impacts of changes in resource quality. A balanced view of these issues requires an understanding of the physical framework in which all human ideas, institutions, and aspirations must operate. Economics, oil and energy return on energy investment. When oil production first began in the mid-19th century, the largest oil fields recovered 50 barrels of oil for every barrel used in the extraction, transportation and refining. This ratio is often referred to as the energy return on energy investment. Currently, between 1 and 5 barrels of oil are recovered for each barrel equivalent of energy used in the recovery process. As the ROEI drops to 1, or equivalently the net energy gain falls to 0, the oil production is no longer a net energy source. This happens long before the resource is physically exhausted. Note that it is important to understand the distinction between a barrel of oil, which is a measure of oil, and a barrel of oil equivalent, which is a measure of energy. Many sources of energy, such as fission, solar, wind, and coal, are not subject to the same near-term supply restrictions that oil is. Accordingly, even an oil source with an ROEI of 0.5 can be usefully exploited if the energy required to produce that oil comes from a cheap and plentiful energy source. Availability of cheap, but hard to transport, natural gas in some oil fields has led to using natural gas to fuel enhanced oil recovery. Similarly, natural gas in huge amounts is used to power most Athabasca tar sands plants. Cheap natural gas has also led to ethanol fuel produced with a net ROEI of less than 1. Although figures in this area are controversial because methods to measure ROEI are in debate. Growth-based economic models. Insofar as economic growth is driven by oil consumption growth, post-peak societies must adapt. King Hubbert believed Some economists describe the problem as uneconomic growth or a false economy. At the political right, Fred Daikel has warned about conservatives addicted to the utopia of perpetual growth. Brief oil interruptions in 1973 and 1979 markedly slowed but did not stop the growth of world GDP. Between 1950 and 1984, as the Green Revolution transformed agriculture around the globe, world grain production increased by 250%. The energy for the Green Revolution was provided by fossil fuels in the form of fertilizers, pesticides, and hydrocarbon-fueled irrigation. David Pimentel, professor of ecology and agriculture at Cornell University, and Mario Giampietro, senior researcher at the National Research Institute on Food and Nutrition, place in the study food, land, population and the U.S. economy the maximum U.S. population for a sustainable economy at 200 million. To achieve a sustainable economy, world population will have to be reduced by 2/3, says the study. Without population reduction, this study predicts an agricultural crisis beginning in 2020, becoming critical c. 2050. The peaking of global oil along with the decline in regional natural gas production may precipitate this agricultural crisis sooner than generally expected. Dale Allen Pfeiffer claims that coming decades could see spiraling food prices without relief and massive starvation on a global level such as never experienced before. Hubbert peaks. Although Hubbert peak theory receives most attention in relation to peak oil production, it has also been applied to other natural resources. Natural gas. Doug Reynolds predicted in 2005 that the North American peak would occur in 2007. Bentley predicted a world decline in conventional gas production from about 2020. Coal peak. Coal is significantly further out than peak oil, but we can observe the example of anthracite in the USA, a high-grade coal whose production peaked in the 1920s. Anthracite was studied by Hubbert and matches a curve closely. Pennsylvania's coal production also matches Hubbert's curve closely, but this does not mean that coal in Pennsylvania is exhausted. Far from it. If production in Pennsylvania returned at its all-time high, there are reserves for 190 years. Hubbert had recoverable coal reserves worldwide at 2,500 times 109 metric tons and peaking around 2,150. More recent estimates suggest an earlier peak. Coal resources and future production, published on April 5, 2007 by the Energy Watch Group, which reports at the German parliament, found that global coal production could peak in as few as 15 years. Reporting on this, Richard Heinberg also notes that the date of peak annual energetic extraction from coal will likely come earlier than the date of peak in quantity of coal extracted, as the most energy-dense types of coal have been mined most extensively. A second study, The Future of Coal by B. Kavalov and S.D. Peters of the Institute for Energy, prepared for European Commission Joint Research Centre, reaches similar conclusions and states that coal might not be so abundant, widely available and reliable as an energy source in the future. Work by David Rutledge of Caltech predicts that the total of world coal production will amount to only about 450 gigatons. This implies that coal is running out faster than usually assumed. Finally, insofar as global peak oil and peak in natural gas are expected anywhere from imminently to within decades at most, any increase in coal production per annum to compensate for declines in oil or eng production would necessarily translate to an earlier date of peak as compared with peak coal under a scenario in which annual production remains constant. Fissionable Materials, in a paper in 1956, 1996, after a review of U.S. fissionable reserves, Hubbard notes of nuclear power technologies such as the thorium fuel cycle, reprocessing and fast breeders can, in theory, considerably extend the life of uranium reserves. Roscoe Bartlett claims Caltech physics professor David Goodstein has stated that metals. Hubbard applied his theory to rock containing an abnormally high concentration of a given metal, and reasoned that the peak production for metals such as copper, tin, lead, zinc and others would occur in the time frame of decades and iron in the time frame of 2 centuries like coal. The price of copper rose 500% between 2003 and 2007 was by some attributed to peak copper. Copper prices later fell, along with many other commodities and stock prices, as demand shrank from fear of a global recession. Lithium availability is a concern for a fleet of Li-ion battery-using cars, but a paper published in 1996 estimated that world reserves are adequate for at least 50 years. A similar prediction for platinum use in fuel cells notes that the metal could be easily recycled. Phosphorus supplies are essential to farming, and depletion of reserves is estimated at somewhere from 60 to 130 years. Individual countries' supplies vary widely. Without a recycling initiative, America's supply is estimated around 30 years. Phosphorus supplies affect total agricultural output, which in turn limits alternative fuels such as biodiesel and ethanol. Peak water. Hubbard's original analysis did not apply to renewable resources. However, overexploitation often results in a Hubbard peak nonetheless. A modified Hubbard curve applies to any resource that can be harvested faster than it can be replaced. For example, a reserve such as the Ogallala Aquifer can be mined at a rate that far exceeds replenishment. This turns much of the world's underground water and lakes into finite resources, with peak usage debates similar to oil. These debates usually center around agriculture and suburban water usage, but generation of electricity from nuclear energy, coal and tar sands mining mentioned above is also water resource intensive. The term fossil water is sometimes used to describe aquifers whose water is not being recharged. Renewable resources fisheries. At least one researcher has attempted to perform Hubbard linearization on the whaling industry, as well as charting the transparently dependent price of caviar on sturgeon depletion. Another example is the cod of the North Sea. The comparison of the cases of fisheries and of mineral extraction tells us that the human pressure on the environment is causing a wide range of resources to go through a depletion cycle which follows a Hubbard curve.